Very good morning. I am Loganathan. I am working as assistant professor in Engineering College. So in this video, I explain multiplication algorithm in computer architecture. In previous video, I explained about binary arithmetic operations, so how to convert integer to binary numbers, and then I explained binary conversions, and then I explained one's complement, two's complement, and then how to perform binary operations, that is like addition and subtractions. So all the with examples. So these things are explained in previous video. So today I explain how the multiplications algorithm perform in computers. So topics, what are the topics today I take? So first topic, multiplications algorithm. Second topic, fast multiplications. Third topic, division algorithm. And fourth one, floating point numbers, addition, subtraction algorithm. So, arithmetic and logical operations perform in ALU units. So the computer can understand only binary numbers, zeros and ones. The computer can perform arithmetic and logical operations, that is multiplications, division, floating point addition and subtractions. So now we discuss one by one how the multiplications are performed and then divisions and floating point operations are performed in computers. So in this video I explain only multiplications algorithm. So in computer architectures, they have three multiplications algorithms are followed. So first algorithm is sequential version of multiplications algorithm. Second one is both multiplication algorithm. Then another one is fast multiplication, that is bit pair recoding algorithm. So in this slide I explain these three algorithms. So remaining next slide I will explain division algorithm, floating point, arithmetic operations. So first algorithm, sequential version of multiplications algorithm. So before go to the algorithm, I first explain the multiplication basic steps in binary. So in multiplications, binary multiplications, they have two parameters, two elements are used. That means two values are used. One value for multiplicand, another value for multiplier. So I will explain with one example. Here multiplicand value is 1 0 0 0. So multiplier value is 1 0 0 1. See the multiplication process. So first the multiplier multiply with multiplicand. So first we take the multiplier least significant bit, that is 1. So 1 we multiply with multiplicand, so we get 1 0 0 0, and then next values take 0, they multiply with multiplicand, so all values are 0. Again next take 0, they multiply to multiplicand, then we get values 0. So because the value 0 multiply with any values, we get a 0. So next value 1, that is most significant bit, multiply with multiplicand, you can get 1 0 0 0. So add the product values, let's say add the product values, we finally we get 1001000 is a final output, that is final product of the given numbers. So it is like a normal multiplications. So we can perform a multiplication of operations in computer. We follow separate algorithms. So first algorithm is sequential division of multiplication algorithm. So in this algorithm, they follow some procedures. That is three basic steps are followed. So first step is they take multiplier. So in this multiplier, they take the least significant term multiplier, determine whether the multiplicand is added to product registers. Here they take then first step, they take decision making based upon the multiplier bit. That is multiplier bit, specifically least significant bit values. So based on the least significant value, they determine the multiplicand is added to product register or not. Step two, left shift the multiplicand register by one bit push. Third step, right shift the multiplier register by one bit. So finally, these three steps are repeated until 32 times to obtain the product. So these three steps are repeated until 32 times. See the block diagram of sequential division of multiplication algorithm. They have a multiplicand, multiplier, and product, and then arithmetic logical, that is the ALU and control test. That means we check the conditions. If the multiplier bit is 0 or not. If the 0 means we can perform some operations. See, what is the here I explain flow chart, how the algorithm are executing through graphical representations. So first start, then test the multiplier values. So already tell you in procedure, first step, check the multiplier value. If the multiplier value is 0 means directly we can shift to the multiple register left one bit position, and then immediately you can perform shift to the left, shift to the multiplier register right one bit positions. Suppose the multiplier value is 1 means add the multiplicand to product register and the place the result in product register. So we can add the multiplicand value to the product register. Final output is again stored to the product register. Then again we can perform shift operations, that is multiple register is move one bit positions. Let's say move one bit positions and then shift to the multiplier register right one bit positions. So this process will continue until 32 times. After complete the 32 time repetitions, the process will be over. That is, the process will be stopped. Now see the block diagrams. See a multiplicand. They represent as 64 bit, and ALU arithmetic logical unit 64 bit. Product is 64 bit. These product is in this base we can get final output. In ALU we can perform arithmetic and logical operations. Multiplicand we give input. Multiplier also we get give an input. So for first foremost step is the multiplier bit position is fine, and check if the multiplier least significant bit is 0 or not. If the least significant bit is 0 means then directly we can shift to the multiplication right side, shift to the multiplication, and then again multiplier shift, then finally go to the condition checking up to this process continue 32 times repetitions. Otherwise, the multiplicand bit is 1 means we can perform addition operations, that is multiplicand plus product register added. Then final output again go to the product registers. So these also and then after the addition, we can perform multiplier shift operations, multiplicand shift operations. So this process continue until 32 times. So now I explain with one examples. See the example. 2 into 3. That means you take two values. 2 into 3. So 2 is a multiplicand. 3 is a multiplier. So two binary value is 0, 0, 1, 0. So I take 4-bit binary numbers, and then multiplier digit number is 3. And the equivalent binary number is 0, 0, 1, 1. So I will explain here. Multiplier equal to 0, 0, 1. Multiplicand value is 0, 0, 1, 0. So see the table. So I explain sequential division multiplications algorithm. So initially we take multiplier. See multiplier value is 0, 0, 1, 1. Multiplicand values 0, 0, 0, 0, 0, 1, 0. So product is 0, 0, 0, 0, 0, 0. See here the multiplier have only 4 bits, but multiplicand product is have 8 bits, because the multiplier bit size is 32, means the multiplicand product is bit size is 64 bit. That's why they add 4 bit in multiplicand and 4 bits in extra 4 bit in product registers. So now start the process. So first foremost step is check the least significant bit of the multiplier. If the bit is 0 means you can perform some operations. If bit is 1 means you can perform additions, and then perform right shift, left shift, then left shift operations. Again check the conditions. If not satisfied, that means then again go to the condition checking. Again perform additions operations, left shift, right shift. This process will continue until 30 times. Here we take only 4 bits. That's all. Here we take only 4-bit binary numbers. Then we can repeat it only 4 steps. We can perform only 4 steps. The iteration will be performed in 4 steps. So when first we can initialize all the values. Multiplier it can also initialize, and then multiplicand product is also initialized. Yes, now start the process. Now check the multiplier values, the least significant value. That value is 1. So 1 means what is the procedure is. So add the product register. See the flow chart. What is the procedure? Multiply is equal to 1 means add multiplicand to the product and place the result in product register. See here, see the value. So what is the procedures? To add to multiplicand to product register, and again place the result in product register. See now add 0, 0, 0, 0, 0, 0, 0, 1, 0, and product register value 0, 0, 0, 0, 0, 0. So we can add these two value. Finally, we can place the value in product register. Then after we can perform additions, we can shift the multiplicand left. We can shift the multiplicand value left side, left 1-bit positions. So here is a multiplicand value. We can shift the left side, that is move to the left side. So left side, after moving, we can get the value as 0, 0, 0, 1, 0, 1, 0, 0. Then after left shift operations, we can perform right shift in multiplier, right shift of multiplier. So we can do right shift operations. So after right shift, we can get 0, 0, 0, 1. So remaining are same. So now we complete the one iterations. Final output of the multiplier, again we check the least significant bit check. Now we check the least significant bit. The least significant value is 1. So again do the same operations. Then that is add the multiplication and product register value and then place the product register place. Again we can perform shift left multiplication operations. So and then third shift right multiplier on the positions. Shift right multiplier on the positions. After second iterations, you can check the multiplier bit values. So this least significant values. Now least significant value is 0. So 0 means no operation. There is no addition operations. Only shift operations you can perform. So shift the left multiplication one bit position. So we can perform the we can finally get 0001 0000. So after completing the multiplication shift operations, we can perform multiplier right shift operations. So after the right shift, we can get multiplier values 0000. Now we can check the most significant bits of least significant bit of multiplier value. That is multiplier value is 0. Again do the same operations. No operation. Shift to the shift left multiplication values and shift right the multiplier values. So now we complete the 4 iterations and 4 iterations because only now we take only 4-bit numbers. So in this example we can they perform only 4 iterations. So final product, so final output we get from product register. So in this product register place we can get 4 8-bit numbers, 8-bit binary numbers, that is 0000 This is a final product value. So the final product value is 00000102. The equivalent integer value is 6. So we take 2 into 3. So we multiply these two values. Finally, we get 6. So finally, we get here 6 values. That is 6 binary number values in 4 iterations. 00000110. So next algorithm, both multiplications algorithm. So compared to sequential division multiplications algorithm, so Boost is a very fastest algorithm because they have in sequential division multiplication algorithm have drawbacks. They will take more steps to complete the multiplications operations. So they introduced Boost multiplication algorithm. Is a fastest multiplications algorithm. It also support as sign number multiplications, sign number binary multiplications. It is also used to speed up the performance of multiplication process, and it is very efficient compared to the sequence division of multiplication algorithm. Both multiplications algorithm also follow some procedures. We see the procedure first, and then move to the examples. So first procedure is take we take m is a multiplicand, q is a multiplier. So we know in multiplication process we need two elements. Then the m is a multiplicand and multiplier. So m is a multiplicand, q is a multiplier. So consider a 1-bit register q minus 1, and first initialize q minus 1 equal to 0. Initialize to 0. Consider a register a and initialize to 0. So here follow some conditions. In this algorithm, they get conditions. If q not q minus 1, already we have q not q minus 1 are same. That is q not equal to 0, q minus equal to 0, and 1. Suppose r q not equal to 1, q minus equal to 1 means we can perform a right shift by one bit positions. Right shift by one bit positions. If q naught q minus 1 equal to 10 means, then we can perform a minus m, that means subtractions, and then perform arithmetic right shift operations. And third condition is if q naught q minus equal to 0 1 means, then perform additions a plus m, and then perform arithmetic right shift operations. So now I explain briefly. So first initialize q a q minus 1 a q minus 1 to initialize to 0 and count equal to n. So count n equal to n here represents number of bit used in the operations. So the second step, based on the value of q naught and q minus 1, do the following things. So already q naught and q minus 1. This is based on the two inputs, we can perform operations. So now based on these two values, they have some they will check the conditions. If q naught q minus 1 equal to 0 0, then only perform right shift operations. That means right shift the q q1 q a q minus 1, and then finally decrement count by 1. Suppose if q naught q minus 1 equal to 0 minus 0 comma 1, then add a and b and store in a. Then perform right shift operations. What are the element we can perform right shift is a q minus 1, final decrement count by 1. Then C, suppose if q naught q minus 1 equal to 1 comma 0 means, then subtract a and b, store result in a. Again perform right shift operation q a q minus 1 and final decrement count by 1. Suppose if q naught q minus 1 equal to 1 1 means, then only can perform right shift operation and final decrement count by 1. So repeat step 2 until count does not equal to 0. See the block diagram of Booth algorithm. This is hardware implementation of sign multiplication, because Booth algorithm support sign multiplications. See this block diagram, multiplication sections. That means is a ALU sections, and then is a Q is a multiplier sections, and then we also have control logic sections, and then q minus 1 and a. See q here q minus 1 is a 1 bit register. You can the initial values, q minus 1 initial values 0. So in this algorithm we take two binary values, so two by bit q and q minus 1. Based on these two values, we can perform multiplication algorithm. Suppose these q naught q minus 1 are same means, you can only perform right shift operations. Suppose q naught q minus 1 values are differ. For example, 1 0 or 0 1 means addition and subtraction operation will be performed. So now let's see the flowcharts. Explain the algorithm in graphical way. So q a equal to initialize a equal to 0. So first start, and then the initialization a equal to 0, q minus equal to 0, b is a multiplicand, q is a multiplier, count equal to n. Then if now check the conditions q naught and q minus 1. Q naught q minus 1 same means only can perform arithmetic and logical arithmetic right shift operations and decrement the count. If q naught q minus 1 equal to differ, that is 1 0 0 1 means 1 0 means you can perform subtractions, 0 means you can perform addition operations. So after completing addition or subtraction, you can perform right shift a q minus 1 and then decrement count values. So again check the condition. If count equal to 0 means then stop the process. If count equal to non-zero means again go to the condition checking. You can perform addition or subtraction, and then finally you can perform right shift operations. This process will be continued until the count equal to 0. So now see the examples. See, previous sequential division algorithm only take positive numbers. So in this example, see the both algorithms support sign numbers. So the sign number is -5 into -4. So these two numbers are sign numbers. So here we take minus 5 is a multiplicand values, -4 is a multiplier value. So before go to the multiplication, that is before go to the algorithms, and the 5 equal binary value will be taken. That the 5 equal binary value is converted to 2's complement value. Then a 2's complement value is assigned to the B register. And then it take multiplier value -4. So 4 binary value will be taken, and then the 4 binary value is converted to complement value. That value is assigned to Q register. So now P register value is 1011. Q register value is 1101. So before go to the algorithm, so first we convert the given sign number to 2's complement. That value assigned to the particular registers. So multiple register is B, multiple register is Q. So now two registers have values. We can now we do the operations. So first step is initialization. So we can assign only 4-bit resistance initial value. Default initial value is 0. So A is initial value is 0. So we can take 4-bit values. Q value already we know, multiply value is Q. So multiply value binary bit is Q value is 1100. So Q minus 1, the initial values, default initial value is 0. So initialization. So first step we can check the Q naught and Q minus 1. So Q naught, Q minus 1 are both values are 0, 0. So 0, 0 means we can only perform right shift operations. You see the right shift. So what are the element we do the right shift operation is A, Q, Q minus 1. So A values 0, 0, 0, 4 zeros. Q value 0, 110. Q minus 1 is 0. So now do the right shift operations. So after right shift operations, we can move all the element to right side. And then second step, uh, so after right shift, the count will be decrement. That is decrement. Then again check the after right shift, we can again check the Q naught Q minus 1. Again same, we get same value 0, 0 and 0. So again we do the same operation right shift the A Q minus values. Then third after right shift decrement, we get decrement values. Then move to the step 3. Then after step 2, after completing step 2, check the Q naught Q minus 1. We get 1 0 value. So 1 0 means what is the procedures? 1 0 means we can perform subtractions. That is A minus B. So after the subtraction, the final output storing A. So we complete the subtraction. Again, we do the right shift operations. See. A equal to A minus B. So A value we know. So A final A value is 0, 0, 0, 0. A B minus B value we know multiplicand values. So what is the subtraction procedures in binary numbers? So subtraction procedure is we take B values and we do the 2's complement, then add with the A values, A register values. And finally we get after we can perform this A equal to A minus B, we get 0, 1, 0, 1. And then Q register value same double 0, double 1. Q1, Q minus is the same 0. So after performing this operation, then again we do the right shift operations. Right shift means 0, 0, 1, 0. This one goes to Q register 1, double 0, 1. Then this one go to Q minus 1. So finally we get these values. So again decrement the count values. We'll go move to the step 4. Before go to step 4, again check the Q naught Q minus 1 value. So Q naught Q minus 1 value are same 1 1. 1 1 means we can perform only the right shift operations. So after the right shift, we get 0 0 0 1 0 1 0 0 1. So final product is the 0 0 0 1 0 1 0 0. It's a final value. So the equal integer value is 20 plus 20. So we get a positive numbers. So now see the fast multiplications. That is third algorithms. So compared to the previous two algorithms, so fast multiplication is the performance very high. Also, the multiplication process will be completed in few seconds compared to the both algorithm and sequence algorithms. In fast multiplication, they use one algorithm procedures. That procedure is bit pair recoding of multiplier. What is bit pair recoding of multiplier means? The bit pair recoding holds the maximum number of sum words. The bit pair recoding holds the maximum number of sum words. That means we take in this fast multiplication, that is bit pair recoding of multipliers, take multiplier value. The multiplier value is reduced in half. Reduced in half. For example, we take 8-bit multiplier means only we take 4-bit numbers, 4-bit binary numbers. 4-bit binary numbers. So the multiplier is reduced into half. That we can see the bit pair recoding covers the maximum number of summaries. So before go to the bit pair recoding of multiplies, you must know the rules in bit pair recoding of multiplies. They follow separate tables. So in the table, only we can specify multiplier bits positions. So you see, multiplier bit position is I plus 1 I, and then I minus 1. So they have 3 positions: I plus 1, I minus 1. So that is 0 0 0 means the equivalent value is 0. 0 0 1 means the equivalent value is 1. 0 1 0 means the equivalent value is plus 1. 0 1 1 means the equivalent value is 2. 1 0 0 means the equivalent value is minus 2. 1 0 1 means the equivalent value is minus 1. That is I position value is minus 2. 1 0 1 means minus 1. 1 1 0 means minus 1. 1 1 1 means 0. So how to convert that means multiply into uh, uh, half. That is, I explained previously. See, I take one binary numbers. That binary number is one, triple one zero one zero, triple one zero one zero. So here, least significant bit, you take additionally one bit. That is one bit position is zero. It's a extra bit we taken for getting by getting multiplier values. So we take first three values. So we take left side first three values 1 0 0. See, one portion is I plus 1, 0 portion is I. This additional bit portion is I minus 1. Now check the table. 1, that is 1 0 0. So 1 0 0 means the equivalent value is 1 0 0 means the equivalent is minus 2. See, minus 2. So again, move to the remaining three bits. That is, I take remaining three bits 1 0 1. So now one position is I plus 1, 0 position is I, one position is I minus 1. Now we can value check with the help of table 101. 101 means the equal value is minus 1. Okay. So similarly, again take remaining three values 1 1 1. Uh, 1 1 1 means what is the value? 1 1 means zeros. See, 0 minus 1 minus 2. So I take only, so I take only five bit numbers, 5 bit binary numbers, but equal multiply value by this we get 0 minus 1 minus 2. So reduce the multiplier values. So you see 5 values, that value reduced to 0 minus 1 minus only 3 values. So after getting the by multiply reduced values, this reduced multiplier value is multiply with the multiplicand. See, and so another examples, both recorded multiplies. So in both recorded multiplies, both vector recording of multipliers have another name, modified Booth algorithms. So I think also another name, modified Booth algorithms. So I explained with one example. That example is positive numbers 13 and negative number 6. So positive number 13 equal binary number is 0 1 1 0 1. So negative number minus 6, we take 2's complement for this minus 6 values. We get as 1101 0 1101 0. See, now we find is a minus 6 is a multiply. Now we find the pair values, the multiplier pair values, the pair values. The equal pair values pair values 0 0 minus 1 0 minus 2. So with the help of table, we can find these values. So previously I explained how to find them these values, equal binary values 0 0 minus 1 0 minus 2. So now multiply with this value to 13 binary values. Certain binary values. See that table. The 30 binary number 0 1 0 1, and then minus 6 equal both record multiply values uh, 0 0 minus 1 0 minus 2. uh, Now least significant values minus 2. How to perform minus 2 into uh, uh, 13 binary numbers? So now take the 2's complement of 0, 1, 0, 1 and then multiply with two binary numbers. So two binary number is two binary numbers into 2's complement of 13 binary numbers. So finally we get these values. Then again multiply 0, again get these values. Again multiply minus 1. Minus 1 means you take 2's complement of 13 binary value and then multiply with 1. Then finally we get 1, 1, 0, double 1, remains are 1. Then again 0, 0 multiply with another 0, 0 multiply with 0. So finally we can add the these values. Finally we found the product of the given multiply values. So final output is final product is 1 1 1 1 1 0 1 1 0 0 1 0. So okay students, so today we discuss about multiplications. In computer architecture, multiplication have three algorithms: one is sequential division multiplication algorithm, booth multiplication algorithm, and then fast multiplication algorithm. So today we discuss three algorithms. So next class I explain division algorithms, how the division operations are performed in computers. So okay, thank you students.